Welcome everyone to the latest webinar from the IET South Yorkshire Local Network, and very good to see Germany and everybody else on board with us. We've got Mike Frain talk to us tonight about arc flash developments in Europe, and to say we're pleased about it doesn't cut the mustard. Mike sits on our committee as a volunteer, as a secretary, but Mike's main role really, he currently consults on a wide variety of electrical subject matters, but he's a nominated expert on the BSI, IEC, T7, TC 78 live working committees. He's also the expert resident on the IEC 78-901 Arc Flash Guidance Project Team. So I think you can see from that he comes well qualified and certainly got the backing of everybody that he needs to. But in addition to that, Mike's past career, it's encompassed a wide variety of roles in high voltage, looking across the supply industry, running projects up to 66 kV, looking in utilities, power stations, DNOs, chemicals, and heavy industry. Mike's also been responsible for some of the more commercial activities around that as well. So he's successfully set up businesses within the utility, the industry, but also successfully set up business outside of it as well in private enterprise. So we've certainly got something that's moving and shaking. But he's held a variety of senior management positions across consulting, looking at contracting, maintenance, and project organisations. And of course, as you'd expect, he's a chartered engineer and a fellow of the IET. So, and from my personal knowledge of Mike, I've worked with him for a while on the committee now, he's a gentleman of the finest order. So with that, I shall hand over to Mike to give us the European approach to arc flash. Have you go, Matt?
Well, thank you for that, John, and hi everyone. I know it's a truly international event tonight, so I'd like to say good morning and also good evening and also good day to you all wherever you are. My name's Mike Frain, and it's my pleasure to take you through this presentation on the European approach to arc flash and latest developments. I could talk about this subject till next Wednesday, so I only have a couple of hours, I'm afraid, so I'll just have to try and cover as much as I can in the time. Just a small amount about myself. I think John's covered it mostly, but just to say I've been privileged to work with an abundance of household names in most industries. But more than that, I've been fortunate to have worked alongside some brilliant people in electrical safety. So blessed, actually, to make some long-lasting and enduring friendships along the way. So why is it that we're talking about tonight? Well, I'll quickly go down the agenda. After the introduction, I'll explain the arc flash phenomena and also spend some time looking at common mistakes, using some of my own experiences. I'll discuss the legislative framework within Europe and then go on to outline my 4P approach to arc flash risk assessment. There's a section on updates on standards, which I'll include some that are fairly unique in Europe, and that's later in the presentation. And then I'll finish off by introducing some solutions and an arc guide. With my qualifications and disclaimer, there are quite a few people that I represent, but none of their views are going to be served on this presentation. I just want to make that clear. Either my views, in no way is it meant to represent the views of those organisations. Furthermore, no liability can be accepted for personal injury or for any other losses or direct or indirect result of the interpretation of my views or any of the standards that are featured here or in future guidance. So why am I doing it? Well, I care passionately about electrical safety, that's the first thing. And I'd like to give something back by sharing my experiences and knowledge. And in fact, back to the electrical industry itself. And that's why I do volunteer in so many roles at the moment. I'd also like to stop having to close stable doors after the horse has bolted. In other words, having to introduce safe working practices after an arc flash event. I've been called in to do that on more than a few occasions, I'm afraid to say. Next, I keep being told that there's a lack of clear guidance about the subject, and that's why I'm active with the standard committees such as the IEC, BSI and IET, and my quest is to be able to provide simple and accessible options for the management of arc flash. And as it says here on your slide, this is my mission statement, I suppose. I've pinched a couple of words from the Institution of Engineering and Technology to inform and influence duty holders, designers and service providers to reduce danger from electrical arcing by providing quick, simple, accessible and accurate predictive tools with practical advice. I'm going to take you on a bit of a timeline. I'm not going to include all my career in here, so you don't need to worry too much. But there's a fair bit to say. If I first of all go back to 1989, that was a year that sort of stuck in my memory for more than one reason. In 1989, I was summoned by the Health and Safety Executive in the UK to attend court as a prosecution witness in the case against an electrician. It was brought under the Health and Safety at Work Act 1974, and the electrician's apprentice had been injured in electrical flashover, or arc flash as it's often referred to nowadays. And I was the first on the scene to take charge and make things safe. It was over a year later that the case came to court, and I remember feeling sorry for the electrician concerned, knowing that he was actually a family man. I'd known him for a few years, but in that time that I was waiting for his case to come up in court, he must have suffered countless sleepless nights as he waited his fate. Thank goodness his apprentice went on to make a full recovery, but I did have knowledge of other electrical flashover incidents both then and before then. And indeed, there were tragic deaths of 2 electrical workers from arc flash at the same company in the late 1980s at Scott Lane in Doncaster. In the same year, that was to give evidence in court, the electricity at work regulations were written and were published 12 months later, and I was involved in writing and publishing new low voltage codes of practice for my company and training about 400 contracting electricians. Roll on to 2007, and I co-authored an article on the subject in the IET Power Engineer magazine with my good friend Jim Phillips, who's presently the IEC International Chair of the Live Working Committee and Vice Chair of the IEEE 1584, responsible for the guide and performing arc flash calculations. The article caused quite a stir at the time among professional engineers and inspired various debates and conferences on the subject in the UK. 5 years later, Jim and I went on to produce a paper called A European View of Arc Flash Hazards and Electrical Safety, and it was presented to an audience of over 500 delegates at the IEEE Electrical Safety Workshop in Florida. So there was a bit more discussion this time from the United States side of the Atlantic, and it's no coincidence, so I'm led to believe, that there was an adoption of a more European-style risk assessment process into the US consensus standard, NFPA 70E, which followed in 2003 on its 3-year cycle. Which brings me to today, and I'll explain later why I've spent the last few years writing guidance and easy-to-use tools and calculators to help duty holders and to keep themselves and those that work for them safe and free from harm. So let's have a quick reminder what arc flash is. Lots of people do know what it is, and I know that we've got some experts on the call tonight, so welcome to those, but there are also those that this might be the first introduction to it, so I'll try and satisfy both parties. So arc flash, what is it? Well, for a start, it's just another hazard. I've been consistent over the years, and The major consideration is to understand it and to root out real danger. The analogy of the hidden tiger lurking in switchgear works for me, as my prime consideration is to identify and evaluate the hazard as the first steps in risk assessment. That's what we're taught to do. And I've used this model many times to explain the phenomena to delegates at various seminars and training sessions. Arc flash is usually caused by inadvertent contact between an energized conductor such as a bus bar or a cable with another conductor on Earth's surface. But simply, it's the insulation breakdown, and very often that insulation in question is low voltage systems anyways, is simply air. Sadly, the cause of the insulation breakdown is very often human intervention. Some of the practical examples that I'll show you later exemplify that. So here we are. If you have a look in the diagram, you can see two copper bus bars that are separated by a 30mm air gap. And then they're connected to a 400 volt electrical source with a prospective short circuit capacity of 25,000 amps. It's a sort of output that you get from a 1000 kVA transformer, I suppose, in an industrial setting. As you can see, there's no protective device, just a switch, connecting the two bus bars is a piece of heavy gauge fuse wire. But you can see that between the bus bars. When I ask electrical workers a question, what will happen when I switch that, close the switch, sorry, they'll often say, well, a large amount of current will flow and the fuse wire will just simply rupture and rapidly disconnect the circuit. Well, actually, that's not what happens. What actually happens is that the fuse wire will vaporize, and in doing so, it'll ionize the air between the two conductors, and that in turn, it creates a low impedance path. Large amounts of current will flow, creating temperatures as high as 20,000 degrees centigrade, so I'm told, which will immediately vaporize any element known to man. There will be massive expansion of air and vaporized conductor material, which causes an electrical explosion. For instance, copper will expand by 67,000 times its original volume in a split second. The thermal effects will cause horrific injuries through burns, ultraviolet radiation, which causes arc-eye, ballistic effects, which can cause blunt force trauma to anybody stood by. Next, I'm going to talk about the consequences of an electric arc flash, and you don't actually need to inquire much further, do you, than just a quick internet search to reveal masses of material, including photographs and videos depicting horrendous arc flash injuries to individuals. Put simply, electrical burns are horrible. They're quite slow healing, very slow healing actually, and they leave long-lasting physical and mental scars. Just recently, an electrical contractor here in the UK was fined £1 million plus cost for breaches of Section 2-1 of the Health and Safety at Work Act 1974. It was following burns to an electrician was undertaking routine testing on low voltage equipment. Then there's another company, and this was only the other day, only 2 days ago when I got to hear about this. And they were fined £660,000 under Section 3 of the same legislation. Again, arc flash on 415 volt equipment, low voltage equipment. So that's not where the losses stand at, I'm afraid. You know, the next one down, I'm thinking about compensation claims, you know, through people taking their boss to court and so on for not protecting them properly and so on. But there's also damaged brand name. You might raise an eyebrow or two there. Well, I was working with a large mechanical and electrical contractor who just had an arc flash incident with one of his people. It became very clear to me actually that after a recent arc flash incident, it could actually threaten the viability of his company because of the damage to his brand. He was working for blue chip companies basically, and this is not a good idea to be prosecuted for an arc flash if an electrical safety is your core competence. And of course we wouldn't argue, I don't think, that electrical contractors, that is what their core competence is. Then there's the losses from severe equipment damage and lost production. That can be eye-wateringly. There can be big figures that never really seem to be taken into account properly. Again, I can hear for the next one on environmental damage, eyebrows being raised. Well, where does that come from, environmental damage from an arc flash incident? I'll just refer you to something that happened to me. I got called out on one very wet Sunday night, in a night in August 1992. I know it's a long time ago, but the fire brigade were just dampening down what remained of their main substation when I discovered that the cause of the fire was an arc flash in a PCB filled high voltage capacitor, polychlorinated biphenyls, by the way. What that is a non-biodegradable poison. It gets into the atmosphere or into rivers or the waters, and you can't get rid of it basically. But it's nasty when it burns as well, and I had to alert the fire brigade commander to get his officers tested for dioxins, and they were all shipped off to the local hospital because of what was given off by the fire. And then I had to arrange for a company to deal with the liquid remains of the oil and the PCBs that were about to be discharged into the nearby river. It was actually the river down at Rotherham. And we averted that by being able to skim all that poison and oil off the top of the bund. Just want to mention, we're just going to go back to prosecutions and fines. And in the UK, there doesn't even have to be personal injury to provoke legal action by the authorities. This comes out of the requirement to report an arc flash event under the UK reporting of injuries, diseases and dangerous occurrences, or RIDDOR. I'll not go through it in detail, but basically if you have an arc flash, it's seen as a dangerous occurrence. I'm going to go through a few slides now that just talk about some my own experiences dealing with clients who've had arc flash incidents, and generally after they've had an incident or an accident of some other sort, that have been involved in writing safety rules and so on for them. And this is one of those occasions. This is one of my closing stable doors that I referred to earlier. And this is a company in the UK, and they've got a guy connecting cables into this 200 amp circuit breaker panel on the left-hand side. It was at high level, so they had to access it using a mobile elevated work platform. And it became this on the right-hand side, for reasons we don't properly know, even to this day. But the fact is, the guy was working on, pulling cables in there, and there's a possibility that there was a manufacturing defect inside the busbar stack within the MCB part of the distribution board. And we think that it could, because of the disturbance, created a flashover within the unit itself. But that, combined with the upstream protective devices not being properly set, meant that once there was a flashover, it carried on flashing over. And the lad, and I say lad because he was an apprentice, by the way, he was in the last year of his apprenticeship, had to jump out of the mobile elevated work platform. So not only did he get burns, but he got fractures as well. This is one of those where there's a mistaken belief that if you can plug it in, anything, whether it's a 13 amp plug or your plug or wherever it might be, if you can plug it in, then it's safe to do live. Well, there's lots of plugs you can do, but not in these particular cases, it's not. On the left, it's an 800 amp bus bar trunking. It's in a bakery. I'll come back to why it's in a bakery in a second. It resulted in injury to a worker some years ago. And I was doing, an audit there. And you can see, I was looking up at this 800 amp bus bar trunking. I could see these burn marks on, where the top-off point was. Trouble is, when I asked what they were, when I was doing the safety audit, I discovered that the current electrical manager didn't have any knowledge of it whatsoever. And they were actually doing exactly the same thing that led to the hospitalisation of an electrician some years earlier. I finally got hold of somebody, one of the old hands, who told me all about what happened, and he was badly hurt by the sounds of it. On the right, there's a 400 amp tap-off unit that I discovered at university. As you can see here, all the back's blown out. It's a long story, that one, but not for today, I'm afraid. The last one is, well, there isn't a photograph of this, but just to relate to this, it came to me when I was putting the slides together. I was doing an arc flash study in the Czech Republic, and I endeavoured to stop some live working on a badly damaged live busbar system. And I was working through an interpreter who said the chief electrician had told him, what does he think I am? In other words, what does me, think I am? An electrician or a baker? So the photograph of the arc flash in the busbar trunking in the bakery, it came in handy on that occasion. It's another one where I was asked to undertake an investigation into an arc flash incident, which caused injury to a facilities technician who had been fault finding on a chiller pump Star Delta motor set. And a big IT manufacturer. The picture on the left is a healthy unit, and on the right is a damaged switch fuse. And my conclusions were that the arc flash started on the load side of the switch fuse, which is there, but it migrated to the line side. How do I know that? Well, all the three fuses were ruptured. And the arc flash was caused whilst on load, which eventually escalated. That's what I thought. And this was backed up by the manufacturer's detailed examination as well. When I turn the unit over, I can see what the arcing damage was caused by. It's caused by low-level arcing across the contacts whilst it was on load, and that eventually escalated. And the reason for that was the damage caused by someone forcing oversized fuses into the carriage and cracking the monoblock. I think you can see that, can't you, at the back there. And as you can see on the reverse, that's what's happened. And look at the fuses. Each one of them is a different size to the other. And somebody's purposely forced that fuse into place and cracked it. This is one where I was called out on a Saturday. Two electricians were supposed to have come into this chemical works, actually, to vacuum this panel out. And there's a Saturday morning. Tell you a little bit more about Saturday morning working in a second, but it's when they could have the power off. So instead of locating the upstream protective device, they thought that they could get away with just operating the local isolator, which is on the front panel there. What they found was that it was just flopping around in the hand, and somebody removed the actuator bar to the local isolate and also removed the phase shields. So they mistook this large but lower current rating switch on the right-hand side of the panel. They mistook that for the main isolator, thought somebody must have retrofitted it or something. I don't know what they had in mind. But somebody had also removed the phase shields inside. They went in to vacuum the panel, and of course they put the vacuum nozzle across the live buzz bars, and the pair of them ended up in hospital that afternoon. It's a sort of accident for me that this should be a case study for a quiz, because or can you spot how many contributory factors? And I think you should go back to school if you find lesson 20 if you knew the whole facts behind it. Another one here, this is not an arc flash, but it could have been one. And I've seen so many instances where screening, phase shields and internal trunking lids have been missing in control panels. And that's why I sometimes yawn when people say we've designed out we designed out the hazard, in the switchgear design, because this is what happens later on. People alter things and carry out unauthorized alterations. And in this particular case, it's a compressor mains panel, and you can see that there's 800 amp bus bars in the bottom there, and there was a lad working in there at the time, which attracted me over to it. And on further investigation, I found part of the shrouding had been left off, and it's actually on the adjacent panel. I think you can see it there. So that was I had to search for it, but that's where it ended up. So you think that was it. The seriousness of it actually was compounded by the conversation I had with a young man who was working inside the same panel. He was undertaking some diagnostic testing with a multimeter whilst on the buzz bars while they were energized. Above the buzz bars, but while the buzz bars were energized. He told me that he worked for a refrigeration contractor who had a contract for the fridge plant at that facility. And actually, on further questioning, it transpired that he had very little experience. He'd at the height of his qualifications, the National Vocational Qualification Level 2, which is fairly low for those people outside the UK. So he should have been there. It wasn't competent for doing anything on electrical systems at all, in my view, and he hadn't got the experience or the qualifications or knowledge. And finally, just in terms of my examples, this last one, this is a common denominator in so many arc flash incidents. It's working on damaged or defective equipment using incorrect or damaged instruments. And you can see there the two fairly badly damaged distribution boards, weathered and so on. They were still live when I took those pictures. On the right hand side, that's an instrument which was involved in an arc flash incident. So, as the saying goes, you can't manage what you can't measure, and I believe that to be true when it comes to managing arc flash. So I would suggest that if we are looking at a proper arc flash risk assessment, we need to first of all identify the hazards, but then evaluate the hazards. How do we evaluate them? Well, we calculate the incident energy, which defines the severity of the arc flash at a certain distance. So it's basically the thermal energy given off by an arc flash. It's measured in kilojoules per meter squared, joules per square centimetre, or calories per square centimetre. Kilojoules per meter squared is a true SI unit, although calories per square centimetre seems to be the favoured currency for arc flash PPE. For today's purposes, I'll probably stick to calories per square centimetre and measure and perhaps think as well about joules per centimetre. But it also governs the arc flash boundary. In this case, 1.2 calories or 5 joules per square centimetre applied to the skin for 1 second is the threshold of the onset of a second-degree burn. You'll often hear about a scientist, Alice Stoll, who did experiments in the Royal, sorry, no, I was going to say the Royal Navy, it's the US Navy many years ago in the 50s, and carried out experiments on live human beings to see what hurt them or not, and came up with this figure of 1.2 calories as being the onset of a second-degree burn. And you'll see a matching on the right-hand side there. Well, if you held your finger in that match for a second, that would be seen roughly as the threshold of a second-degree burn, besides hurting a bit. We also use that to govern the arc flash boundary. So I'll explain that in a little bit more detail in a few minutes. IEEE 1584 is the guide for performing arc flash hazard calculations, and it's probably the most comprehensive means to determine incident energy. And it's internationally recognised, and it's also an auditable standard. So that tends to be the most popular. I'll show you one or two other ways of actually getting to an incident energy level and determining PP and so on later. So the last one, I'll try and explain it very quickly for today, but arc thermal performance value refers to PP. It's a measurement of a fabric's or PPE. It might be a fabric, it might be other, clothing like gloves or whatever. It's the ability to protect an individual from a burn due to exposure to an incident energy level resulting from an arc flash. Basically, it means that the incident energy will be attenuated to 1.2 calories per square centimetre, or the onset of a second-degree burn. So specifically, if we were to design PPE, the ATPV allows us to provide a measure by which the fabric will limit the amount of thermal heat on the outside, on the inside of the arc flash wear down to 1.2 calories. So to try and explain that a little bit better, and I haven't there, but if you bought an 8-calorie boiler suit, for instance, if you had 8 calories of incident energy on the outside, that would attenuate that down to 1.2 calories at skin level. So what affects arc flash severity? Well, is a fairly ubiquitous industrial distribution system with a transformer and a switchboard, main switchboard, and out to a control panel or another switchboard or wherever we're actually going to work on. And if there was an arc flash at that point, what affects the severity of that arc flash is, first of all, the arcing current, and is directly proportional to the arcing current. So if you double the amount of current that flows into the arc, you double the amount of thermal energy from that incident. Or if you halve the amount of arcing current, you halve that. And that's all worked out from system, system configuration and impedances and so on. The other factor is time. Arcing current we can't do a lot about, but time we might be able to do something about, because that's worked out from the protective device at that point, which supplies that piece of equipment. So again, it's directly proportional to time, the incident energy level. So if we halve the amount of time through lowering the protective device settings there, it'll lower the incident energy level by a half. So what else affects severity? Well, first of all, distance, and we'll talk a bit more about that. The relationship between distance and incident energy, it falls exponentially. It's a good reason to stay away and keep as much distance as a risk control measure. Secondly, the geometry, the conductor geometry and containment, in other words, how is it in a box or is it in open air or whatever. So breaking that down, it's a configuration of the electrodes is important, the intensity of electrical arc and the resultant level of incident energy. It's affected by the electrode configuration. Horizontal versus vertical conductors will make a difference. Talk about that later. Open air versus enclosed will make a difference. The size of the enclosure will make a difference. And how the conductors terminate will make a difference. And also the gap between conductors. Don't think it takes much imagination to know that if you increase the gap, it'll actually reduce the amount of arcing current. But that's all those items are all calculated or taken into the calculations for IEEE 1584, which I mentioned earlier and I'll refer to later again. So here we go, this is an incident exposure level. And as you can see here, this chap is standing at a working distance. It's a working distance from the arcing source that we take into account when we're looking at incident energy levels. And it's normally measured to the torso and the head. And the result of that is historically, that's where the measurements are, because the severity of a burn is affected by the amount of the body which is affected by the burn itself. So as it happens, the more of the body that is burnt, it lowers the survivability rate, as does age, by the way. So me getting into an arc flash instance is not a good idea, I don't think. And then I mentioned arc flash boundary. What's this? This is quite a good and important measurement, actually. And from IEEE 1584, it says an arc flash boundary is a distance from a prospective arc source at which the incident energy level is calculated to 5 joules per square centimetre or 1.2 calories per square centimetre, that magic figure, onset of a second degree burn, if you remember from my earlier slides. That's what an arc flash boundary is. And what that means is that, well, it has a particular meaning within US consensus standards, but what it means is that stood outside the arc flash boundary, there should not be no injury whatsoever. Stood inside the arc flash boundary, we've got to start thinking about other measures to protect the person. The other thing that I'll mention, because this might crop up depending on how much time we've got today, is something that's called the 2-second rule. Because quite often arcing faults, they can persist for longer than 2 seconds actually, and the longer it persists for, the larger the amount of heat energy from that. But if we're talking about personal injury here, we've got to think about how long that person's going to be stood in front of the incident itself. And as it happens, within IEEE 1584, they cite 2 seconds clearance time as being how long a person might remain in the location of an arc flash incident. And I mentioned the German standard, the GGUV guide, and they use a 1 second rule actually, rather than a 2 second rule in there. So it goes to show actually that it is a bit of a rule of thumb, and it's not in tablets of stone whatsoever. And of course, what you can't do is apply this if you're constrained in any way by a trench or by a mobile elevated work platform, the like that I mentioned earlier on in the presentation. So this brings us on to the legislative responsibilities in Europe. Well, the news is there are no specific requirements for arc flash hazard assessment, but that doesn't get us off the hook, I'm afraid. What there is the EU directive. It's often called the Framework Directive 89391, and it requires employers to perform risk assessments for all hazards and tasks. In the UK, similarly, we require that risk assessments must be suitable and sufficient. And all that refers to is that we should be looking for hazards that could cause harm to individuals and evaluating the amount of harm that may be involved in that before we look at how much damage that could cause to somebody. In particular case, an arc flash, do the sums. That's what I'm leading to. And then in both those documents is the principles of prevention. That is in the UK Management of Health and Safety at Work regulations. And there are 9 principles of prevention in there. And the first 3 are avoidance of risk, an evaluation of risks that can't be avoided. So in other words, by quantifying it, by some calculation or other, and then combating the risks at source, and so on. This is my simplified approach to arc flash risk assessment. We've got the usual hazard, likelihood, and risk. And we know if we've got high hazard, high likelihood, there's going to be high risk. If we've got high hazard but very low likelihood, it's likely that the risk also is going to be low. So hazard, in this case, it's derived from system parameters. So it's about the impedance of the network, about protective devices, and so on. The likelihood, however, that's derived from what you're actually doing there in the first place. What is it? What is the task? And what are the system conditions, the environment? What about the equipment itself? Does it look like some of the equipment I've shown to you earlier? Has it been damaged? Has it been properly used? Has it been maintained properly? Are you using it in the way that it's meant to be used? Like the plug-on unit that I mentioned for the bus bar system earlier. When I contacted the manufacturer of the modern system that was on the right-hand side, they confirmed to me that whilst bus bar trunking systems that they produce gives flexibility to the user, they're not meant to be plugging large 400 amp devices on live. So this comes into the task, doesn't it? And out of that, derived from that, is the hazard and likelihood becomes a risk. And here we go with my 4 Ps approach to risk control for arc flash. It appeared years ago, actually, and I've modified it a few times since then, but I think I've got it about right now, so I'll stick to this one. In this case, we've got 4 segments, starting with predict in red there, which is about calculating or validating the level of incident energy level that we can expect. Prevent is about using the risk control measures and the hierarchy of risk controls that I'll speak about later. Process is about policy, rules, procedures, and so on, before we go into the protect segment, which is all about residual risk and optimum solutions. And why I've used those words is if we've done all these first 3 properly, when we get to protect, we either don't need protection, or the protection that we're providing is comfortable PPE and optimum solutions for the worker, and we're not putting people into very heavy PPE where they don't need to be. Not saying there's no place for heavy PPE, but in a majority of cases, I would suggest that. So here we go. I've got a little bit of flow chart takes us around this. So first of all, we predict the severity using IEEE 1584 or one of the other measures that we have. We create results from that. And from that, we then go into prevent. So in green there, can we apply prevention techniques? And the question is, can we apply further prevention techniques? If we say yes to that, then we have to reevaluate. So we go back to predicting the severity again, recalculate, creates more results. And once we've exhausted the prevent step, we can then go on to the safe working practices, or process as I call it here, looking at safe people, safe procedures and safe places. And it's the guide that I've referred to earlier, huge section on process, and talking about risk assessment and so on, and about human factors and so on, that we'll talk about later. And then finally, we've done all that. Hopefully we apply protection measures that are of a residual level, or to cover the residual risk of optimum solutions. So we first of all now into the the second part of this, which is the prevent segment. And this deals with the hierarchy of risk control measures, which I've got down the right-hand side, and it deals with the first two. So I'm going to deal with prevent, but also minimisation in the next few slides. I can't cover this in massive detail because of time constraints. As I say, I could go on, but I'm going to try and cover the majority and just flick through 1 or 2 slides just to show you what I'm thinking about. First one's elimination of live working. Reducing protection settings, I've got a little bit to say about that. Improved protection scheme, something I could highlight. Again, it's in my book, in the guide, so there's quite a lot on that. Arc detection, active internal arc suppression, and I've got a slide on that. Switchgear design, holistic approach to system design, and operation sequence, slide on remote operation and non-intrusive diagnostics. So there's a lot there which I'm not going to hope to cover tonight. So you'll just bear with me, I'm sure, to try and go through this as quickly as I can. Elimination, testing for dead in order to make safe. It can expose a person undertaking isolation to the hazard. And it's a bit of a thorny issue, actually, and it's something I deal with a lot in the book itself. Again, I mean, there's 7 pages on just testing for dead, because it does carry a risk. It still needs a high level of risk assessment and competence of the individuals. And we can start to think about designing out the risk through segregation of power and control, by safe control systems, protection by barriers, built-in test points and so on. But there's a lot that the individual can do to protect himself. I'm going to use a second example on that list I started with on prevent. And in this case, I'm going to demonstrate the most commonly used technique for lowering the severity of an arc flash, and that is adjustment of upstream protective devices, certainly low voltage systems. In this case, it's a protection curve for a commonly used 400 amp thermal magnetic circuit breaker, and you can see there it's got opening and clearing times on the same time current curve. So we're looking to the right-hand side basically to clear the fault. In this particular case, it's got instantaneous pickups which are adjustable between 5 and 10 times, and it's set at 10 times the rating, so at 400 amps. It's set at 4,000 amps, the instantaneous setting. But what we've got here, we've got a arcing fault, which is 4,300 amps. So taking into account the protective device settings and so on, that will disconnect in 1 second. So the fault will persist for 1 second. The next slide, I'm suggesting we can start to think about lowering the instant energy level, because as I'd said earlier, that if we lower the time to trip by a half, we'll actually lower the instant energy level by a half. And in this case, we're going to move the magnetic protection settings over to 6 times rather than 10 times. So in the next slide, you can see that the same current of 4,300 amps, it's resulted in 0.02 seconds disconnection. So rapidly, instantaneously, in other words, the fault is going to be disconnected. So actually, by the action of a twist of a screwdriver, we just lowered the incident energy level by a massive 50 times. So that's very common. Clearly, we can use it only when, for permanent situations where it's safe to do so, where it doesn't have a problem with discrimination or interfere with the load that's on that particular equipment. On the same vein, sometimes it's not possible to alter upstream settings on a permanent basis because of protection coordination issues, but interactions with energized equipment of any description, it will inevitably lead to some sort of risk. A solution might be to temporarily alter the instantaneous settings on circuit breakers for the duration of the work and then put them back again. But this in itself, it does require carefully thought out processes to ensure that maintenance settings are not left behind after the work is completed. Eaton, the manufacturer, recently patented a system that they called Arc Flash Reduction Maintenance System, ARMS for short, and there's images there on the right-hand side showing how it works. And basically at the top there, you've got the front of the protective device, and that setting there sets the maintenance mode for that particular device. And what happens in blue there, that's the normal setting for the device. In red, that's a maintenance setting, and it's done roughly what's happened in the previous slides, isn't it? That's something that I think will be quite popular in the future. So I'm going to just flick through 1 or 2 photographs of prevention techniques, internal separation, and this particular board, the outgoing device that are brought out to external cable boxes, so there's insulation and barriers between the outgoing terminals and the bus bars within the units themselves. Fully insulated bus bars, while on the left-hand side they're not insulated at all. Doesn't take much imagination to see that an arc flash, particularly if there's vermin that gets in there, is far more likely on the left-hand side than it is on the right-hand side. Lots to say, but not for today on MV and LV internal arc protection. There are within the IEC standard, it happens to be 62271. For high voltage switchgear, there are standard characteristics, to test equipment itself, but as of yet, none of that is mandatory. You have to ask for it, basically. I'll just talk for a few minutes about this one. This is arc detection and arc suppression. Sometimes arc detection is used on its own without the suppression to trip up upstream devices. I've come across that several times. But several manufacturers now have produced innovative ways of reacting to an arcing fault by effectively creating a zero impedance short circuit across the bus bars of equipment. Yes, you heard me right first time. They're going to make a short circuit across all three phases and sometimes to earth as well. So dependent upon the method used for sensing the development of an arc, they can be incredibly fast, and manufacturers claim disconnection times as low as 4 milliseconds. As you can see from the diagram, they consist of a CT and that picks up through the optical detection units as well. It picks up the arc development. So simultaneously, when the arc detection units pick up ultraviolet light from the arc at that point, at the same time, the CT picks up the rise in incident energy, the rising current. And within 4 milliseconds, the earthing and shorting switch will apply an earth and make the equipment safe. And an upstream device either trip of its own accord or be sent separate tripping signals to disconnect as well. LV remote switching is another thing that clearly people are asking for this more and more. On the left-hand side, you can't quite see him, but he's holding a lanyard to remotely switch some equipment. On the right-hand side, this is a retrofit, basically. It's a mobile unit that you can rack equipment in and out with. I'm not going to spend too much time on this, but it's another subject area I can speak about for some time. I often hear engineers telling me that they've designed out the arc flash risk at design stage, but what they're really referring to is the switchgear design, which matters, but it's not the whole story. A holistic design approach needs to look at the design philosophy and also the operation and maintenance of the equipment, who's using it and how and so on, even take into account some of the competence issues or lacking competence issues that are referred to earlier. And the sort of things that I might think about distribution philosophy, example like size and number of paralleling of transformers, and operation and maintenance, removal of shrouding and so on. Which brings us on to the process segment. Bottom left there, you can see the 4 Ps again. So we're in process at this stage, and we're going to look at policies and procedures. And as you can see on the hierarchy of risk control measures, they appear further down the hierarchy for obvious reasons. But what I would say is, and I'll keep saying this, is that I'm finding that people get into trouble because they have got absolutely no idea whatsoever of the danger that lurks within switchgear. Going back to my analogy of the lurking tiger, I suppose. And I think information and training at a very early stage would give a step change on attitudes towards arc flash itself, particularly with electricians. So Talked about safe people, competence, information, training, instruction, and supervision and control, which will be required in measure if we're talking about lower order hierarchical measures such as PPE. Supervision and control is needed more and more. Where we're at the top of the tree, supervision and control becomes less of an issue. As far as Outflash is concerned, safe places means well-designed and documented installations, maintenance, operation, I suppose, as well, but have confidence in the protection. Is the protection system going to operate? Because if we are going to calculate instant energy on the basis of an upstream device actually operating, I think we really need to have confidence that it is going to operate within the time that we've set. And then finally, safe procedures, having a risk assessment process, specific rules with clear responsibilities and people that are authorised to carry out that particular work. Next is, again, process. Talk very briefly about this. Again, we're looking at written rules and supporting procedures. And the guide describes in safety in great detail, as mentioned before on that particular subject, but clearly defined written instructions are the main thing. Listing out not only what somebody can do, but what they're not allowed to do is a good start when we're dealing with the arc flash hazard. Individuals must have clear responsibilities and competence assessments, and that means contractors as well. I wanted to mention the importance of human factors, and time pressure and tiredness, particularly towards the end of the shift, can be a really vulnerable time. And we talk about human factors quite often as a bit of an academic exercise, I find. But practically speaking, it is a surprising factor, common factor, that I've come across on more than one occasion. And it's like the one I referred to earlier in the chemical works about the two guys who vacuum a panel out on a Saturday morning. It's carrying out high risk activities out of hours that are normal on normal days off. And I've come across it several times, and I can, if I can paint a picture of what I'm trying to drive at on this, a non-shift working team who comes in on a Saturday morning. This might sound as if I'm really stereotyping now, but they come in on a Saturday morning. Maybe Friday night is the usual night out and not be as bright on a Saturday morning. Maybe it's a football game on a Saturday afternoon, so the time pressure's on and it's self-generated, and they want to get away for the football and so on. So, and finally, I think we've always got to be vigilant to the possibility that the person could be intoxicated through alcohol or drugs from the night before. Not a good mix when working near energised conductors, that is for sure. Within processes, the signs and labelling, risk assessments need to be recorded. And that's a mandatory requirement. But from the risk assessments, it may be that we're looking to field mark equipment as well. The European standard is Directive 9258, and that's into our own UK safety signs and signals regulations. It talks about colours and symbology that affect all signs and signals for use in Europe. Which will take into account some of the language barriers as well, by the way. So signs and symbologies are quite important within a European context. But arc flash labelling, it's not a mandatory requirement, unlike some of the consensus standards, particularly US NFPA 70E, where it's mandatory to field mark equipment. The European approach is one where it's less prescriptive, let's put it that way. provide safety signs, yes, but only where there's a residual risk, where we've not been able to remove the risk by other means, if there's a residual risk, that is. So there's got to be a significant risk to health and safety of workers and others. Does it mean that I'm advocating don't label switchgear? Not at all. I think, but it needs to be highlighted within the rules and procedures as a requirement to remove residual risk. And finally, signs and signals that don't comply with the European directives, such as ANSI Z535, it can't be used within Europe and UK now. We've left Europe. Just on the right-hand side, that's the colours and symbology and some examples of signs used in Europe. On the left-hand side is a ANSI label. On the right-hand side is a warning label, which has been provided courtesy to me from Electrical Safety UK Limited. So thank you for that. We're finally now into protecting the individual against residual risk. And in this case, we'll look at making sure that we've got all of the measures in place before we even contemplate PPE. I'm not going to go into this in a great deal of detail because it deserves perhaps another occasion to do so. But the directive within Europe is 89656, and European countries adopt their own PPE standards from that, so their own secondary legislation. And within Great Britain, it's a personal protective equipment at work regulations. And in Northern Ireland, that's 1992, in Northern Ireland, they've got their own, which were provided in 1993. The main thing for me is user acceptability. And within the guide, there's a section on utilities, a separate section on utilities. And I had the fortune to be able to help Northern Power Grids to put in their PPE requirements, and they did a fabulous job on providing acceptance from the users themselves, and they engaged with the workforce right from get-go to finally providing the PPE for people that were working on live equipment. So everyday workwear is something I would suggest, if you've got an arc flash instant energy level on particular equipment, which even at low level, perhaps consider that, particularly because non-arc flash clothing can ignite. So I would always push people to, if they have got those risks within their workplace, is to consider everyday workwear. Consider additional protection on top of that, and hands, head and eyes, don't forget that hands are going to be much closer to the source of the arc. From that same directive 89656, it clarifies that assessments of PPE shall involve an analysis and assessment of risks which can't be avoided by other means. And what I've done is I've put this flow chart together to try and see if we can understand it a little bit more. And basically, the first part of it in box A there is the analysis and assessment of the risk, which is what we've carried out. But then it's about defining the PPE characteristics. And it's at that point we've got to think about how we do it, taking into account other risks and other environmental conditions. I work with a large IT manufacturer, for instance, where environmental conditions meant that they needed high order clean room protection, which was very, very difficult to obtain for arc flash at that time. And we had to work even harder on the prevent area of, or the prevent step, to make sure that we engineered out all the dangerous conditions on that, in that particular site. The other thing is other risk, and you know, that they might be involved with. So defining the PPE characteristics at that point, and then compare PPE characteristics in A to in B with availability, which is we go to the market at that point. And I put this together because I think you know, it's not a case of saying, yeah, I want a 7 calories shirt or something like that. It's what's available out there, and also there may be requirements that we have to just think through in terms of you know, availability as well. Bearing in mind that there are different types of fabrics which tend to perform quite well together, but you know, there's inherent permanently treated fabrics, and there's also there's also inherently flame resistant fabrics, you know, and the two are different. I'm led to believe nowadays that the treated fabrics are have got much more longevity, and at that point we choose a PPE. Now I'm going to just talk to what's new on standards, and within IEEE 1584, for people that are fully aware of this, I apologise, but there is a higher degree of accuracy. The last print was 2002, which is a long time ago, so this has been coming a long time, but the higher degree of accuracy because of a larger number of tests, and it takes into account new electrode configurations. There used to be 2 electrode configurations back in the 2002 one, you know, either in a box or in air, but now there's 5. I'll talk about those in a second. And adjustment factors for enclosure sizes have come in now, and they've dropped the distinction between earthed and unearthed systems with the new reprint. And finally, the arcing current variation factor has come in, whereby before there was an 85% correction factor. And what that stands for, what we mean by that, is at low voltage in particular, it's important to carry out an incident energy level calculation, but then apply an 85% correction factor to lower the arcing current down, which will lower the arcing current, obviously, but it may increase the amount of time it takes to trip. And paradoxically, that could actually create the conditions where the instant energy level for the lower level of arcing current could be higher. One which is very European, I've got to say, is the instant energy limit, which has been brought into the IEC standard for PPE. And this, if you recall, I talked about ATPV, you know, being the measure for PPE. Well, this is a different measure, and this is a requirement that's required in PP, particularly if you want to get anything sold in European organisations, you know, so through CE marking. So incident energy limit, ELIM, it's the numerical value of incident energy attributed to a product or material below the values of all product responses below the Stoll curve. Remember, we were talking about this Alice Stoll earlier. She created a Stoll curve where there's a 50% chance with a ATPV, now there's a 0 chance. It's because all the values are below that stall curve, so there isn't any chance of a second degree burn. So put simply, Elim differs from ATPV in so much as that there's a 0 chance of a second degree burn. So there's, rather than a 50% probability. But when it's applied to a garment, I understand that this additional safety factor from people I know, they have said that it would lower it by about 10%, derating for the garment. So it could be 10% heavier, I suppose. That's the other way of looking at it. It's seen as a bit of an academic measure by lots of people because ATPV would have to be exactly equal to the actual arc flash to create the conditions for 50% chance of a minor burn. Not in my practical experience, I'm afraid, that one. I've done thousands and thousands of arc flash calculations in the field, so I've not really come across those conditions myself. Next is the DGUV guide, which is based upon an algorithm which was theoretically derived from a box test method for evaluating PPE in accordance with the PPE IEC standard, which is 61482-1-2. The one that's used predominantly for creating an ATPV, as I suggested earlier, is what's called open arc testing. This is box test, and it is used predominantly in Germany, but it's a very simple test actually, which is similar in setup to the example that I gave at the beginning. Can you remember, the two bus bars that were facing each other, 30 millimeter gap? Well, the box test is 30 millimeter gap. It is a 400 amp supply, single phase supply that goes to it. So it's fairly easy to create, and it happens that one of the bus bars, well, as I remember, one of the bus bars in the box test is aluminium actually, and the piece of clothing or fabric is held 300 millimeters or 12 inches away from the arcing source. So the output from that test is created through two particular parameters, and that is for the PPE to withstand either one of two parameters. The first one is 4,000 amps for half a second, or 7,000 amps for the same period. And what they do is create an arc protection class, APC1 or APC2. And the algorithm compares the arc energy for the actual work environment against the equivalent arc energy or the protection level that I've suggested earlier. So they're both expressed in kilojoules. So if you get an arc, if you get an incident, if you get the equivalent arc energy, which is higher than arc protection 1, but lower than APC 2, then you would wear PPE according to APC 2. Obviously, they don't provide incident energy calculations, and you can't make a direct comparison between the DGUV standard and IEEE 1584. But it is in use within Germany, particularly, and France. Next one is the US standard. I thought I'd mention this because there's lots of clients that I've worked for that are of US the they're from the US, the US owned, that's the word I was looking for, the US owned. And an FPA 70E is a consensus standard. It's requirements for safe working practices to protect personnel by reducing exposure to major electrical hazards. I would say that, the earlier NFPA 70Es that I was relating to did have a requirement from going from hazard straight into PPE, and the likelihoods was missing. Now that is not the case, and I actually think it's a good document. It's not as big as people think it is. I mean, it is actually only 19 pages on the safety related pages, but it is predominantly about hazard elimination and being the first priority. And this has been brought right to the forward within the document itself. And there's new examples of risk reduction methods in there when testing absence of voltage, which I referred to earlier, and also at within the informative indexes, there's a new article regarding capacitor safety, which I found very interesting indeed. So I talked earlier about the IEEE 1584 electrode configuration and enclosure sizes, and I've reproduced some of them, well, all of them here, so to let you have a look at them and what they actually mean. The first one is what we call the VCB configuration, which is vertical conductors within a box, basically. And this actually appeared in the 2002 version, and it uses 3 equally spaced vertical conductors within the box itself. And actually what happens in practice is the arc is driven away from the source of supply and downwards to the bottom of the enclosure and arc and out. So you can see what the arc looks like. That it's forced downwards and out towards the worker. Next one is VCBB configuration. I'm sorry, but I've put the wrong slide up there, so you'll have to take it from me on this one. I'm really sorry. But on the left-hand side, that should have shown a barrier across the bottom of the of those particular conductors. And VCBB stands for vertical conductors in a box, but terminated into a barrier. So what happens in this case, and this is what's been demonstrated, so you'll have to use your imagination to see a barrier across there. What happens is when the arc hits the barrier, then the plasma cloud is driven out then towards the worker. And the configuration on the right-hand side is called HCB, which is horizontal conductors within a box. And they're pointing outwards inside a metal enclosure. It's particularly aggressive, this particular configuration, as the plasma from the arc is directed outwards from the ends of the electrodes and directly at the worker. I saw a demonstration of this years before it appeared in the standard. I saw it in IPH laboratories in Berlin, probably about 8 years ago. Well, more than that, probably about 10 years ago. And it is pretty aggressive to see in the flesh, there's no doubt about that. And then the next ones are in air. And the first one, VOA, is in air configuration, and HOA is in air, but a horizontal configuration. VOA was in the 2002 edition, by the way. The HOA configurations, it's similar, but as you can appreciate, the thermal effects radiate out towards the worker in the case of the horizontal configuration, and tend to be a little bit more aggressive. So this is just an extract from the guide, but I wanted to show you what a VCBB one looks like in terms of something in the flesh. So if you can see there, you've got an air circuit breaker, and the conductors terminate directly onto the top of the, in other words, straight into a barrier. That would be called VCBB. So, just want to talk about fault level because I mentioned a paradox, and actually, some years ago, when I was doing some work for utilities, it came as a real surprise to the engineer there that, in fact, this is a quotation, wow, who would have thought that I would have been in more danger 460 metres away from the substation than directly outside. Well, it was from a seasoned distribution engineer who were actually looking at live jointing on 400 amp and 500 amp 185 waveform cables, so he thought that the incident energy level would be highest directly outside the substation. Of course, it wasn't. It was highest nearly a kilometre away, and that is because low fault currents can sometimes persist for longer periods, and because of that, even taking into account the 2-second disconnection time, it creates conditions where the incident energy level can be massively higher for lower fault currents. And if you have a look on the right-hand side, I first came across that and named it the short circuit paradox back in 2009, I think it is that, in the Electrical Review, where I wrote an article there, the short circuit paradox. And the understanding is that it might seem blasphemous, but to a power engineer, but at low voltage, fault level can actually be your friend. And rapid disconnection of dangerous arcing faults can be the order of the day to protect workers. So what happened to good old I²T then? Well, nothing has happened really. What I've demonstrated so far is that it depends upon the current and the time. So it happens at low voltage arcing current is less than prospective fault current anyway, which will increase the disconnection time. So with a bit less, but a lot more T, there will be a dramatic increase in energy let through. And then finally, next few slides are coming on to the solutions. And this is in the guide that I've provided, and the buzzwords I've got there on the right-hand side is, I wanted this when I set out doing this a couple of years ago, for it to be simple and accessible. And I think I've got there to a point where it's taken a lot of work, and I'm sure that labour will not be paid back in full anytime soon. But at least it's at a time when I can put that out. It's web-based, and it's going to be available for phone, tablet, and for PC as well. These aren't finished yet, but this is a typical incident energy calculator. Normally these two boxes aren't shown. This is all you need. You can choose electrode configurations there on your right hand side. And all the voltage, this goes up to, this particular case is based on IEEE 1584, goes up to 15,000 volts. And it went to disconnection times within that panel there. But what we've also got on the right-hand side is a calculator to provide contribution from motor fault, which is quite important, if particularly if all the equipment provided from that particular panel that we're looking to predict the instant energy level on is provided by motors, because there will be a significant motor contribution back into the arcing fault. So that takes care of it quite simply and quite nicely. And this other table, this is where you can enter all your own figures rather than a preset set of figures that you can just click on down here, like for low voltage switchgear or high voltage switchgear or wherever it might be. So I keep talking about fault level, but the question is, well, how do you find it? Well, another part of the practical guidance that I gave is to try and tell you how to get it and how important it might be. That we have accurate figures in there. And the first thing is by calculation. In order to carry out calculations, you need to know the prospective short circuit current at the equipment to be worked on, don't we, at that point? So that is the case whether it's for calculations to IEEE 1584 or the German box test DGUV that I referred to earlier, or even PP if you want to use the shortcuts from NFPA 70E standards table. Still need the fault current and the disconnection time in that case in order to come up with PPE. And also by inquiry, if somebody is providing the power to the site, the person to tell you what the fault level is to that site is going to be the host distribution network operator, refer to them here. And then measurement, I mentioned measurement. You can measure arcing, you can measure prospective short circuit current, but not with a basic earth loop impedance tester, particularly if you're very close to a transformer. You need a piece of kit that is capable of an accuracy. In this particular case, it's made by Metrel, and this is a very high current adapter which is capable of accuracies down to plus or minus 5%. And calculations can be carried out. This is a particular ubiquitous distribution system, and that's out of the calculators that we provide. Actually, I think I've provided a picture of that later. And when it comes to working out the parameters for ArcFlash, I've created what I call ArcFlash management by exception, a tiered approach to instant energy estimation. And this is on the understanding that most industrial and commercial sites, the vast majority of incident energy levels are going to be below 1.2 calories at a working distance, certainly of, let's go back to that, a working distance of 450 millimeters or 2 feet or 1 feet 6 inches in imperial measures. And in this particular case, they would be called tier 1 circuits. So it's where the incident energy level is below 1.2 calories. And within the guide, we can tell you what circuits they are. And you don't need fault level either to work those circuits out. There's caveat or two to take into account, but that's all explained there. Tier 2 circuits are where incident energy level is below 1.2 calories at the equipment, above a named fault level. And I'll explain that. You might not know what that means until the next slide. Tier 3 circuits, we need just a fault level only to work that out. So we need an accurate reading for the fault level at that point. And then tier 4 circuits, we need the fault level, and we will need a time current curve at that point. And the reason I've put them into that sort of pyramid is because, as you can see from that, the tier 4 circuits are very much smaller than the rest. And I would hope, from a duty holder, that's the concentration that he'll have to use. So this is a tier 2 method that we put in, and these are simple fuse charts. And what this is a 400 amp BS88 fuse. The DIN fuses are very similar, but there are separate DIN fuses as well. Predominantly, they are the IEC fuses that are in use across Europe. And I understand that BS88s that standard is starting to be used in the US, by the way. Somebody might put me right on that one, but I understand that the fast-acting devices themselves are in use over there. But if you have a look at this graph, what we've got is a plot of incident energy level against fault current along the bottom. And 80,000 amps, by the way, is the maximum withstand capacity of a BS88 fuse. But as you can see, the vast majority of the curve is above 10,000 amps. So what you do know that if it's below 10,000 amps, that is where we've got a danger zone. That's where we've got to start thinking a little bit more carefully about what the incident energy level is actually going to be at that point. But it gives a quick and easy yes or no to whether it's whether we're in the danger zone or not. So there's range of configurations. I know it's counterintuitive because what we're saying is that fault level is your friend, from my early remarks, and at low volt it is. But it's exactly the same for shock protection. That your enemy in shock protection is impedance, which is exactly what reduces the arcing current by the way. So, you need to have fault current in order to disconnect circuits within the required times for shock protection. The third one is tier 3. And in this particular case, all that we need is a fault level, and what it is, it's for circuit breakers. And it's the method that I've put together, which allows circuit breakers, as long as that they appear on the system, and we're going through this very quickly, but what we're looking at is making sure that the disconnection time, where the instantaneous is switched on, is taken into account, and that produces a incident energy level and an arc flash boundary. And it's just simply after we've put the circuit breaker detail in, but I'm thinking here about system data, 400 volts, like the previous example, or wherever it might be. We look at the circuit breaker. Is the instantaneous switched on? If it is, then is it listed on the drop-down menu? If it is, yes, we go on to the next one. Does a circuit breaker trip instantaneously? You don't have to answer that. The calculator does. And the results are there, the instant energy level for that particular circuit breaker acting instantaneously. Alternatively, if it's switched off, or the circuit breaker is not listed, or it's the circuit breaker doesn't trip instantaneously, then a 2-second disconnection time will apply, and then we still get a result, but it will be a massively increased result because it's based on 2 seconds, not an instantaneous one. So finally, as the tier 4 circuits, I think I've described the prospective fault current calculator, which is exactly that. It allows you to get an accurate high voltage and low voltage incident energy level and arc flash boundaries does include motor contribution, as I've suggested. There are other calculators there, and not all listed, but there's blast pressure, fault level, which is shown on sorry, that's shown on the bottom there, the prospective fault current calculator at that point. My PC was sort of hiding it off the screen there. There's also other tools to use to help people to get a TCC. So there's a IDMT, inverse definite minimum time, like relay to IEC and ANSI standards. There's a curve creator there, so you put whether we're talking in extremely inverse, the time set multiplier settings are then put against the current settings on the graph. And then there's a DGUV box test algorithm, and there's DC as well in that. So I'm coming to the end, you might be pleased to know about. I just put myself in the shoes of a duty holder, I suppose, that's seeing this stuff for the first time or contemplating it for the first time. So where do you start? Where do I start managing the risk? Well, for me, as soon as possible, ASAP. That's the principle. Start managing it straight away. You don't have to wait for anything to manage this if you follow the following principle. First of all, awareness. And as I suggested earlier, this can this is about awareness of the hazard itself, and which can make a difference, that people know what they're dealing with. Secondly, stop, which is stopping high-risk activities, stop custom and practice behaviours, issue clear and firm instructions to prohibit the above. So it might even be stop, we do not connect cables into live equipment anymore, something that might have been custom and practice at one time. Next is audit, take stock. I've produced audit sheets that allow people to take stock of switchgear and control panels and to identify high hazard equipment. And from that, then the duty holder can start to think about the policies and the procedures and people and places. So look at asset improvement plans and replacement, and then decide on system studies. It may well be that you feel that this needs to go to a specialist, which is fine. But within the book itself, I explain all that, what questions to ask. If you want to do it yourself and you're looking at providing complex software to do studies, well, that's there as well, to make sure you're choosing correctly, from my own experience. And lashes on my back, by the way. So there we are, and there we have it. So what we learned, well, above all, let's know what we're dealing with. Is there a tiger in there? What I'm saying is we won't know without doing the sums. So thank you very much indeed for your time. Just before I finish, I'll just mention that the art guide will be out early next year, just in case anybody's asked a question about that. If you don't want to be contacted, that's absolutely fine. Just let us know. And there's also a CPD certificate for tonight, and it's available from the IT. Just drop me a line on my email address there, michaelfrain@aol.com, and I'll make sure that it's dealt with. And anything else that you want to ask as well, that's there. And in terms of questions and answers, I can say that there are questions and answers straight after this, but if I don't get to answer them all, that's not a problem. Or if there's questions I can't answer, I'll make sure that I do any required research, and I'll answer them in due course. And they'll be in writing, and they'll appear on our IET website. So thanks very much indeed for your time.